afternoon again. Get you to take your seats. That would be jolly and dandy, as they say in the old country. All right, so our next presentation is again part of this theme of the broad-based of knowledge and of issues that we wanted to present at today's forum. And again, talking about standards, talking about componentry, talking about the armouring, and talking about the training, all critical elements of what makes up a successful, fit-for-purpose civilian armoured vehicle. And so the next presentation we have, and also coming on then this afternoon with Theo, is that of mobility. And again, you can have the best built vehicle, the best protective armour, the best trained drivers, but if the brakes fail, there's only so much training that will help you when the vehicle is careering, God forbid, out of control because the brakes don't work, the suspension doesn't work, etc., the tyres, etc. So we thought it'd be a good reminder. We've had a discussion on brakes. I think it was the very first year that we ran the CAV Forum. And we thought it's a very good idea to bring it back onto the agenda. And we're very pleased that Sascha Lucas from MOV'IT will join us today and really go into some of the technicalities and the attributes of the braking system and its impact on the mobility characteristics and therefore the safety of the civilian armoured vehicle. So we're very much looking forward to your presentation. Sascha, take it away.
Thank you very much. Well done. Thank you. Thank you very much, Rob, for your kind introduction, and also thanks very much for being such a great host in this very unique event. Organization and process is really marvelous. So I'm here to talk about brakes in the next 30 and 35 minutes. Welcome and thank you for attending. Before we dive into the details, let me ask you, who of you is a driver of a car, a motorcycle, or a bicycle? Excellent. We all are, right? We are all familiar with braking. We all have experience with almost crashes, little fender benders, and maybe some more serious stuff. Okie dokie. So let me take you on a journey into a world of braking where we will come across a brake awareness part. We will cross-reference to brakes in armored vehicles, and I will try to give you my personal outlook on changes to be expected in the next 5 to 10 years. And on our way through the presentation, we will also demystify the one or the other urban legend about brakes. A quick who is who. My name is Sascha Lucas. I'm the operations director of MOV'IT High Performance Brakes. We are a medium-sized company in Germany, Limburg, just under 20 people. We have been founded in 1995, celebrating our 30th anniversary this year. And since day one, we are developing and producing high-performance brake systems for sports cars, for race cars, for armored vehicles, of course, for military vehicles. And we also supply brake system components like wheel cylinders, master cylinders for a company that since recently is called Armoured. Before that, I think they have been renamed like in July, and before that they were named Continental. You might have heard of them, one of the biggest OEM automotive suppliers in the world. And I'm very happy and also a bit proud that they trust in our production quality since more than 20 years now. In the context of civilian armored vehicles, I would like to highlight that in 2014 we partnered with Dutch company TSS as our exclusive global sales partner. The company is today represented by their managing director Louis Huizen and by Leonard Alkemade, well-known gentlemen among the attendees, as I guess. Now let's get started. If you get in any car that is new to you, if it is a new company vehicle, a new private vehicle, a rental, whatever, one of the first things you probably do is you adjust the seat, the steering wheel, the mirrors, and nowadays also the entertainment, or rather the communication system. And once you start happily driving, you get used to the characteristics of the car. Let it be the steering, the acceleration, and of course the braking. And when it comes to braking, what we all expect rather unconsciously is consistency of the system. That means repeatability and reproducibility. Repeatability, if you apply the brake, you expect the same deceleration, the same braking behavior with every application. Reproducibility means if you are sitting on the passenger seat, then another driver is driving the car, you expect the brake to perform the same way he applies the brake, the same way you did before. So repeatability, the repetition of your activity; reproducibility, the repetition of another person. If you fancy 3-letter abbreviations, you could memorize 3RP, because consistency comes from repeatability and reproducibility, resulting in reliability and thus predictability. And if something is predictable, you don't think about it. It becomes an automatism, right? And how do we achieve this consistency? Now let's have a look at the basic setup of a braking system. One key component, of course, is the brake at the actual wheel. It consists of the brake disc and the hub, and the caliper housing the pistons and the pads. Excuse me. By the way, in today's presentation, I will focus on disc brakes only. There are drum brakes, of course, in the field. The Toyota J70 is an excellent example. Great platform as a basis for up-armoring, and it applies drum brakes at the rear. And with electric vehicles, we see even a renaissance of drum brakes at the rear. But today, because it's the majority in the field, we will focus only on disc brakes. Another key component is the actuation system, consisting of the braking pedal as the actual man-machine interface. This is where you place your foot and where all the action begins. And then you have a booster, either vacuum-based or electronically supported, that amplifies the force of the foot and activates then the plungers in the master cylinder to displace the braking fluid into the braking system. If we expand then the sketch to a full vehicle vision, it looks like this. You have your disc brakes at the wheel. You have your actuation element with the pedal, and you also have your stability control system, and if needed, you have a vacuum pump to support your booster with the according vacuum. What happens now when you as a driver, or we as drivers, see the need for deceleration is you place your foot on the pedal, you push the pedal, the booster amplifies the force, the plungers in the master cylinder are pushed forward, pushing the brake fluid into the brake circuit. The brake fluid pushes the cylinders, the pistons in the calipers against the pads, pushing the pads against the rotating disc. And this is actually where some magic happens, because there is friction between the pads and the rotors, and then the deceleration starts because of the friction, turning the velocity of the car into temperature. In other words, speed is turned into heat. To shed some light on what I just said, let me take you on a brief excursion back to school, back to physics. That might not be your fondest memory of school, so I will make it as brief and easy as possible. You may remember that there is this law of conversion of energy, saying that there is no such thing as energy loss or energy waste, but it's always a conversion from one form of energy into the next. So, like you might remember, I mean, if you drive a bicycle, you're probably old enough to still have a dynamo applied at night to change the kinetic energy of the wheel into electricity and to light up your way. And the same goes with the windmills, changing or converting kinetic energy of the wind and the rotors into electricity. And you can also have chemically bound energy, like in fuels and explosive. And using fuel, you can accelerate a car. And if you blow things up, for sure, you also have heat and speed. So also there you have this conversion of energy. These are the formulas, how you calculate the energy. Don't bother with it. The relevant thing is the unit at the end of the formula, because it's both in joule, and this is the unit of energy. So that's basically just to make sure it's the same thing. I think that's it for this slide. Now, if I would want to give you a more tangible approach, we could talk about boiling water. If you want to heat up 1 liter of water, you need an amount of energy of 334 kilojoules of energy. That is a material-specific value, just like density is, like the specific weight. Breaking down an armored car of 5.5 tons from 100 kilometers an hour down to 0 converts energy of 2,100 kilojoule, or in other words, you could boil 6.5 liters of water with that amount of energy. Now think about how long it takes you to break a car down from 100 kilometers an hour to 0. Depending on the conditions of the road and the conditions of the car, it takes you less than 4 seconds, right? And remember how long it takes your kettle at home to boil up your cup of coffee. It's a tremendous amount of energy that we are dealing with when we are using a car and when we are braking. And with armored cars, it's even higher. Now, I talk about this because the brake system must deal with this amount of heat, which is created by the friction between the rotor and the pads. So pads and rotors are our key players in that energy conversion. They must gather all the heat and dissipate it. In both cases, as quickly as possible. You want to stop as quickly as possible. You have to convert the energy as quickly as possible. And you need to get rid of the energy, of the heat in your braking system, also as quick as possible, which is called dissipation. That means distributing the heat into the surrounding environment. That is supported by the design of the disc. So you have inner ventilation channels, like here, where cold air is sucked in and then taking out the heat from the rotor. It is also supported by gross drills or slots. And also the sheer mass of the system supports this energy management because the heavier the rotor, the more energy it can absorb, it can store before it reaches a critical temperature level. Let's have a look at some real-life examples. Earlier this year, we had the chance to compare several braking systems one by one in identical vehicles. We had 4 VR7 armored Land Cruiser 300s, each weighing about 5.4 tons. Now, for this particular test, we did 10 consecutive stops from 60 to 0 kilometers an hour with a moderate deceleration of 4 meters per square second or 0.4 g. If you do a full stop, pedal to the metal, then you are able to achieve roughly 8 meters per square second. That's usually the value when your ABS kicks in. So 4 meters per square second, it's a decent braking, but it's still a moderate one, okay? We considered this test to represent a hurried rush through a city area. Now the right-hand part of the slide shows the results of the car with the original brake system, a 5.4-ton vehicle, mind you, while the left-hand part shows the result of the car with our MOV'IT heavy-duty system. It becomes obvious from the graphs that both vehicles were able to do these 10 consecutive stops without bigger issues. You see the orange lines, the orange lines on the graph are quite similar. We have achieved the 4 meters per square second with every stop, no problem. What you see if you look at the chart of the temperatures is that the OEM brake has a higher temperature on front and rear brake. We are at roughly 300 degrees with the MOV'IT system and at roughly 400 degrees at the front axle with the OEM system. And if you look closer, you will also see that the difference, the temperature difference at the rear axle is even higher. It's about 140 degrees. And why this is so, we will see in a minute. In the next slide, we see what happens if the heat is not dissipated quickly enough and the brake system reaches a critical temperature. In this next test, we stopped the cars repetitively 5 times from 100 kilometers an hour to 0 with the maximum possible deceleration. That means both feet on the braking pedal. What we can see is, in general, a higher temperature in both systems, but the OEM system is no longer able to provide the high deceleration after the 3rd stop. You see the possible deceleration decreases, and this phenomenon is called fading. It comes from a thin layer of gas that starts to come up because of sorry, I have to repeat it. The reduction of friction comes from a thin layer of gas between the pads and rotors coming from volatile materials in the pads. Let's have a look at pads. Pads are made up from up to 40 different ingredients. It's a true chemical miracle. You have abrasive materials like steel fibers. You have exotic things like potassium titanate to increase the abrasion. You also have lubricating materials like graphite. In some of the pads you still have copper. It's more and more reduced for environmental reasons, but you still have it. And you have cashew particles, of all things, as a lubricating material in your pad. There are also fillers and reinforcing fibers like aramid or mineral fibers. And there are binders like phenolic resins to hold the whole mixture together. And these resins become volatile when reaching a certain temperature, creating that gas layer between the pad and the rotor, reducing the friction. So brake fading is usually the first thing that happens when your brakes become too hot, when your brake system is overheating. And it's quite an uncomfortable thing because suddenly a fence, a wall, or a car is coming closer despite you slamming the brake pedal as hard as you can. I should mention that fading is reversible. Once you are able to cool down the brake system, then usually you reach again the same friction level as you had before. if you have the chance to cool down the brake system. Constant heat also affects other parts of the brake system, and here we see a sketch of the path of the heat. In one direction, it is from the rotor to the ventilation channels, where it is dissipated quickly. In the other direction, the heat travels from the rotor through the friction material, the steel backplate of the pad, through the piston, into the caliper, and into the brake fluid. So what also happens when your brake system becomes too hot is that the brake fluid starts boiling. That is, there are gas bubbles in your pressurized hydraulic system, causing an instant loss of braking power, which can result in even more severe and critical situations when your vehicle becomes uncontrollable by your brake pedal, and not uncontrollable by the driver, but also by the stability control systems, because they also are not able to create the pressure that is actually needed to decelerate the car and avoid the crash or drive you safely through a curve. The threshold temperature for brake fluid to start boiling or gassing out is depending on the type of brake fluid you are using, .3, .4, and so on, but also on the water level in the brake fluid. Brake fluid is a great stuff. The downside is it is hygroscopic. That means it attracts water from things like air humidity. So if you operate your car in a hot, humid Southeast Asian country in the rainy season, you can have more troubles as if you are operating it in a hot and dry country. And this characteristics of brake fluid, the hygroscopic one, is one of the reasons that it needs to be monitored regularly. Every fleet manager will agree to that, I guess. And it has to be exchanged regularly. As we also know from our private cars, when we visit the workshop, every 2 years you should exchange your brake fluid, and sometimes more often depending on the area you're driving at. And of course, the more water is inside your brake fluid, the lower the boiling temperature, the easier you have a problem with braking. Now, finally, when the heat becomes too much for the system, you don't have the chance to cool the brake system down because you are in an escape situation and I don't know, then the system starts burning, and I'm talking about fire and smoke. The volatile gases are no longer only reduce the friction, but they actually start burning. And if that happens, then your pads are turned into crumbles. The rubber parts in your brakes are damaged, like the dust boots, but also the seals, maybe even the brake hoses, causing leakage. And then you have quite a good chance to become a sitting duck with your protege, and probably not a relaxed one as the fellow in the picture. So the conclusion, in a nutshell, is brakes are heat sinks. And the faster and or the heavier the cars become, the bigger the mandatory diameter and mass in order to avoid fade and maintain consistency, or 3RP. To emphasize the obvious, a brake system for an armored car is not a simple upgrade. We must consider a brake system specifically designed for the armored vehicle of the choice. The system offers components that are adjusted to each other to deliver the best performance output. Larger brake discs in both diameter and width. Ventilated brake discs for the front and the rear axle for heat management. Pads with a stable friction coefficient across a wide range of temperatures for providing higher fading resistance. stiffer calipers in both material and design. Exchange your aluminum calipers to calipers made from cast iron, because that provides less flex under pressure. And you also need reinforced brake hoses withstanding highest pressures and also providing less flex, because consistency. I talked earlier about the demystification of urban legends. Here's the first one. The legend says, bigger brakes will stop you faster. The truth is, if everything else remains the same, they won't. They will just lock your wheels faster. Because the relevant factor for the shortest possible stopping distance is the traction between the tire and the road. Once this is overcome by the braking force, then this will just lock your wheels and ABS is triggered, but it will not stop you faster. In this context, a couple of years ago, Lennart Alkemade gave a presentation during this forum presenting the golden triangle of armored mobility. And this golden triangle consists of heavy-duty brakes, of course, heavy-duty tires, and heavy-duty suspension. So bigger brakes alone will not do the job. It's always a combination of these three factors. So the conclusion, the demystification is bigger brakes will not stop you faster, but they will remain cooler during those braking maneuvers. And this goes for armored cars as well as for non-armored cars, of course. Now, how does this all affect civilian armored vehicles? If we start a design of an armored car from scratch, we can consider in our design an approach that covers both lightweight and safety, as Nir Khan showed us in his presentation last year. When we talk about CAVs, however, we usually refer to standard serial production soft skin cars that are then turned into armored cars by adding different measures to increase bullet and blast resistance. Those different measures are, as you all know, steel armoring added to the body of the cars, the doors, the roof, the hood, and the tailgate. Steel armoring added to places where there is no steel in the original car, for instance, to protect the starter battery. Bullet resistance glass in exchange for the original window glass, special passenger compartment in the rear to give the protégés a last resort or a castle keep. And then I'm not talking about added electronics equipment, blue lights, fire extinguishers, intercommunications, and stuff like that. So we add mass. There is no approach for lightweight whatsoever. And this leads to a tremendous weight increase of a serial production Land Cruiser 300, for instance, that has a gross vehicle weight of 3.2 tons in its original condition and is, after armoring, between 5.4 or up to 7 tons, which is an increase of the kinetic energy of more than 100%. Thus, the brakes need to manage that. The next point is that at soft skin cars, the split of mass distribution between front and rear axle is usually around 60% at the front and 40% at the rear, with the engine most times being the highest mass concentration, while all other masses are either lighter or more distributed and less dense, like seats, windows, and so on. So the center of gravity of soft skin cars is slightly further towards the front axle, and also in the middle line of the vehicle, not on the side, but I'm sure you know that. In armored cars, the weight increase distribution is not even. It is rather, we can consider that rather the rear part of the vehicle being more affected by the armoring than the front. Usually the protégé sits at the rear, and so the car gains in proportion more weight towards the rear. Plus, due to the armoring of the upper half of the upper frame area, like the windows, like the roof, there is also a considerable mass added towards the upper end of the car, which shifts then the center of gravity of an armored car from the position of the serial production car more to the rear and also higher. That influences the dynamics of the vehicle. Daniel mentioned that in his presentation, like rolling or swaying when driving through curves or during a lane change, which makes, of course, need for advanced suspension and tires. See the golden triangle. But it also affects the braking behavior because the rear axle must cover the additional weight plus also the change dynamics. And this is particularly relevant for everyday driving. With your standard braking maneuvers, see the city traffic examples that we showed earlier, where we had the higher temperature difference at the rear axle. Let's talk about dynamics. When you apply the brake at any vehicle, doesn't matter if it is a car, bicycle, or even a tank, the laws of physics apply in form of inertia. And this inertia makes you and every other object lean forward. This applies to cars, motorcycles, or bicycles. The front dives into the suspension while the rear travel out of the suspension. And this is due to the weight shift initiated by the inertia. So metaphorically speaking, the front becomes heavier while the rear becomes lighter. By the way, depending on the added mass by the armoring, the increase of the brake system may also demand for bigger wheels to provide the according space to fit the new brake system. So OEM wheels may no longer be capable. With a changed weight distribution of an armored car, the rear brake must grow bigger in proportion compared to the grow ratio of the front brake. And if we do a comparison of the increase ratio of the OEM and the, I was too fast reading, sorry. So with a changed weight distribution of an armored car, the rear brake must grow bigger in proportion compared to the grow ratio of the front brake. If we do a comparison of the increase ratio of the OEM and the MOV'IT Super Duty system, then we will see that in order to adjust the brake balance, it will be insufficient to just upgrade the front brakes because of the proportionally higher weight increase at the rear, which in consequence then demands for an adopted brake force distribution and thus a proportionally bigger increased rear brake, as you can see on the slide. Like we grow the diameter of the front brake rotor by 8.5%, while we increase it at the rear by 14%. And the same is with the brake thickness. And this then in consequence leads to a higher fading resistance due to the weight, or maybe a higher heat capability because of the weight increase to the figures you see at the bottom of the slide. So in this context, the test results shown earlier, where you clearly see the higher temperature at the rear with the OEM system and the fading. Let's go on and demystify another urban legend. The legend says 6-piston brakes are mandatory for armored vehicles, and this superstition is solidified in tenders of issuing institutions and their purchasing departments. The truth is, the number of pistons is entirely irrelevant. What counts at the end is the total surface size of the pistons. Why is that so? Because physics. What the formula expresses is that the effective brake force, FB, is a product of your friction value mu, that's a characteristic value of your pad, and the normal force that presses onto that pad. And this normal force is a result of a rearranged pressure calculation. So in physics, pressure is force per area or force per surface size. And then if you rearrange the formula to calculate the normal force, it's a result of your pressure in your braking system and the area this pressure is working on. And if we do a direct comparison of two competing applications, a 6-piston caliper and our MOV'IT counterpart, which has only 4 pistons, being a 4-piston caliper, then the total size of the surface is a summary. I will spare you the math. At the end, the result shown here is that the 6-piston caliper has a smaller surface of the pistons and hence a smaller brake force than the actual 4-piston caliper. So the explanation for this urban legend is simply physics and proper design. You do not need a 6-piston caliper. Before we come to the final chapter, and I know I'm already exceeding a bit of my speaking time, sorry for that. I hope you're still, your hunger still allows for it. I would like to draw your attention to testing, certification, and homologation. It's of immense importance that the brake system installed of the car of your choice is specifically tested and thoroughly tested. In the European Union, we are using the ECE R13H. It's most relevant since all armored vehicles operating in the European Union must pass this test. PAS 301 is also an accepted testing procedure created specifically for armored vehicles, while the R13H regulation is for every vehicle operating in the EU. So let it be your Vauxhall Astra or your Armour TLC 300, it doesn't matter, they have to pass the ECE R13H. And while this PAS is an accepted test specification, there are some significant differences between those two specifications. While both regulations demand a cold test as a benchmark, a hot test, and a recovery test. Recovery means your brake goes to several temperature profiles. The ECE regulations checks also the secondary brake system. That means if your booster fails, or if one of the circuits of the brake circuits fails, like in an ambush or whatever, then you can still operate the car and you can still break it down controlled. Less performant, of course, you only have one brake circuit left, but it's still controllably being able to be stopped. And last but not least, the ECE also demands for a parking brake test, which might also be relevant depending on where you park your armored car. You don't want it to roll away unconditionally. Now this is, as Rob said multiple times today, this is dear to my heart. Whatever specification is applied, whether it is an ECE test or a PAS or FMVSS or whatever, the accountable vehicle builder and the company that conducts the test, they must ensure that the brake system is properly bled before the tests. That means all air must be evacuated from the brake system. And especially with a TLC 300, as an example, this can be a pain in the neck because of the electric parking brake at the rear axle and because of the electromechanical booster. There are bleeding instructions of the car makers, analysis software and bleeding programs, and they must be obeyed to. and they must be followed thoroughly at all costs, and better 2 or 3 times before the tests, because don't rely on experienced personnel telling you they are doing that since 20 years, they don't need to change their method. They do. Do not apply alternative bleeding procedures or alternative software different from the OEM's original released version, whether this is TechStream from Toyota or BMW ISTA, or I'm sure there are a lot of, every car manufacturer has its own software. Please do it, apply it. I'm speaking here of personal experience because our MOV'IT brake system for the TLC 300 has passed now 4 times several tests, ECE and PAS 301. And every time the first trial was not successful because of supposedly insufficient brake performance. And every time we talked to the according tester and we said, did you bleed it appropriately? Yes, of course we did. Did you apply the TechStream software? No, we have an alternative software. No, please do it with TechStream and do it 2 or 3 times. Better being safe than sorry. And every time they did it, we passed the test without problems. Even 7 tons were not a problem. So bleeding is really essential, and it becomes more and more difficult with these electromechanical systems. Coming to the last portion of the presentation, I would like to give you my personal outlook of possibilities affecting the area of brakes in the next, let's say, 5 to 10 years for standard and for armored vehicles. Now, for sure, electrification is the one topic that without doubt has had the biggest impact to our mobility and the way cars are designed and driven. Electric drive for armored cars is probably not around the corner, at least not in every area of the world. But what we can see today already is the electrification of the braking system. The Land Cruiser 300 is and also other cars, they no longer use a vacuum brake booster, but they use an electromechanical actuation unit combining master cylinder, booster, and stability control system. It's called the one-box solution. You see here 3 different examples from 3 different brake system manufacturers like Advix, Bosch, ZF. They all are developing this stuff and they are all applying that stuff. The introduction comes with a separation of the brake pedal, the man-machine interface, with the actual brake circuit. So that means the driver no longer actually applies a hydraulic circuit directly, but the pedal travel and the pedal speed is measured while the driver is pushing against the spring, a pedal simulator. And then the readings of the sensors are then translated into an according brake pressure and application speed, and this is prepared and provided then by a pump and an accumulator. This increases the complexity of the system, as you can all imagine. And it also increases the number of mechanical parts that are in your hydraulic circuit that are surrounded by brake fluid. And it means the more mechanical parts you bring in there, the more air traps you have, which then again has an influence on your bleeding result. So this is why I'm riding on this point so much, because it can then impact not only the brake testing, but more importantly, the brake performance in the field. There are, of course, advantages. Your brake pedal characteristics can be influenced by software, and you have lower installation cost which is very attractive then to the car manufacturer, of course. But like I just said, more mechanical parts increase the complexity of the system. I do believe that as we have seen with the transfer or transversion from internal combustion engines to now more and more electric drives, this hybrid system, more electromechanics in your brake system, that is only a hybrid solution, like I said, and it leads at the end to electromechanical brake systems without any brake fluid. ZF or ZF has announced at the beginning of this year their first big contract where they are going to supply a fully electromechanical rear brake that is in combination with a hydraulically operated front brake. It all goes under the name of brake-by-wire. That's the magic word that makes everybody nervous in the braking industry at the moment, globally, no matter where you are. And we earlier talked about the fact that CAV are mostly based on serial production soft skin cars. So this will be a future challenge for guys like us, brake manufacturers all over the world, to develop mechanical brake systems for these armored vehicles that may apply an electric drive, at least in those areas where you have the according charging infrastructure. What is the lessons learned, the takeaway from this presentation? First of all, physics rules. Second, brakes are heat sinks. They are turning speed into heat, managing the heat and dissipate it. Bigger brakes will not stop you faster, but they will remain cooler during the same braking maneuvers. The number of pistons is irrelevant, and testing the brake system is in the according car is crucial. Ladies and gentlemen, thanks very much for your attention. I hope you found that interesting and maybe also a bit entertaining. If your hunger allows for it, I'm here for questions. And otherwise, just drop an email to info@movitbrakes.com, or let's have a talk later. Thanks very much.
Okay, so thank you so much. For me, it was marvellous to actually learn more about the technology involved. And if I can ask, I'll ask one question, if I may, is, again, one of the urban myths or issues of potential dispute, that of slotted discs and their benefit for dissipating the heat, and whether that is something that should be on an armoured vehicle or is not necessary. Did you have some thoughts you could share with that?
So slotted or cross-drilled discs are beneficiary for the heat management because they allow either the heat to dissipate, or they allow the gas layer, talking about fading, to evaporate between the pad and the rotor. So having some sort of surface structure, some sort of topography on your brake rotor should definitely help to improve the braking performance.
Will it then also have an impact on the life of the pad, because it's now not being pressured against a smooth surface, but a topographical, as you've just said?
Slots rather than cross drills, probably, but it all depends also on the design of the slots. You can create the slots with a chamfer or with a radius, and then the shaping effect of slots is reduced, while you still have the benefit of getting rid of the gases. So it might have an influence, but not necessarily like rubbing off your pad significantly earlier.
Okay. No? Okay. All right, fine. I think maybe their stomachs are talking more than their brakes along the way. So, look, it's a critical part of the vehicle, and as a systems engineer, it's yet again one of those components that is focused. There's always a focus, but I think that it's more to some extent assumed, or there's some folklores associated rather than the technical information. So thank you so much for sharing it. A small gift to say thank you so much for participating. Please thank Sascha for his presentation.
Thank you very much.